was their result that was supposed to be presented today. He did a ton of work for this conference, and he's sort of missing out because he's expecting. As in last week, he was expecting to have a baby, and he's still expecting. So this is, this is getting tense for him. But anyway, so anyway, I thought it was unfair to them for him not to be represented. So I'll just present his talk for him in my best way I can, and so don't just skip. And if I found a video, then I would have put it on, but I didn't find a video. Okay, so anyway, we're very happy to have Theodore Bordy to present the null mean curvature flow and MOTS.
Well, good morning, everybody. I'd like first to thank the organizers for the invitation and give me the opportunity to give this talk here. So the title is Null Mean Curvature Flow and MOTS, and everything I'm going to talk about today is joint work with Kristen Moore. Okay, so as I'm very into geometric flows, let me first explain what mean curvature flow is. So if we have a surface, we say that the surface moves by mean curvature flow if it moves with speed equal to the mean curvature vector. This flow is such that the surface reduces area as fast as possible. And the equation for such a surface, so if I have an embedding, so we're just going to look at hypersurfaces. So if I have an embedding or an immersion in general of a hypersurface in a manifold M, of an n minus 1 dimensional surface in an n dimensional surface M, we say that this moves by mean curvature flow if we can write this. Okay, where this is the normal, the unit normal to the surface, and h is the mean curvature, the scalar mean curvature. Okay. So standard example of this is that of a sphere. If I look at a sphere in Rn, then under mean curvature flow, the sphere is going to start shrinking and eventually disappear to a point. Okay? And this actually happens in finite time. Now, mean curvature flow has a lot of physical applications and a lot of geometric applications. The one we'll focus today is the fact that mean curvature flow can be useful to detect minimal surfaces. Minimal surfaces are surfaces that satisfy mean curvature equals 0, and these are critical points for the area functional. In other words, a minimal surface is such that if I do small deformations, the area will go up. Okay? So for example, say we have a manifold that looks like this, and here I have a minimal surface. Mean curvature flow could be used to do the following. If I start with a surface way out here, flow it by mean curvature flow, hoping that the equation is such that it lives for all time, then the surface will go and approach the minimal surface. Okay? And the hope is that if the flow exists for all time, then taking a limit as t goes to infinity, your surfaces, they converge to a minimal surface. Okay? So this is a way of detecting minimal surfaces, and actually this is a way of detecting stable minimal surface. Okay? So recently there is a lot of work on the min-max method, which is another method looking to find minimal surfaces, but min-max is used to find minimal surfaces that have an index. Okay? Where's mean curvature flow? Okay. Now, what is now null mean curvature? Well, we're going to do the same thing, but now in a Lorentz space. So I'm going to look at a Lorentz space, and inside this space, I'm going to look at an initial data set. Okay, so G is the metric. M is a space like n plus 1 hypersurface. and K is the second fundamental form of M inside L. Okay. Now, minimal surfaces in this setting have a different form. We're gonna have, instead of mean curvature equals 0, we're gonna have no mean curvature equals 0. Okay, so H equals 0 is replaced by H plus P equals 0. Now, what is P? P is a trace of K, the second fundamental form, over sigma. Okay, so this is the trace over sigma of K. Okay, so this here is the no mean curvature. Okay. So people are interested in these surfaces because they somehow act as boundaries of black holes. So it's an interesting problem to try to detect these surfaces. Okay. So no mean curvature flow now, we're going to flow by this speed. So let me draw a picture. So this is M sitting in L. N would be the unit normal of M into L, the future directed unit normal. And I look at a surface here, sigma, inside M. Okay, so this is M plus 1, this is n-dimensional, M plus 2. And nu is the outer pointing unit normal of sigma inside M. Okay. Now the no mean curvature, as I said, H plus P. H here is the mean curvature of sigma seen as a hypersurface inside M. Okay. And this guy here is the mean curvature of sigma seen as a codimension 2 surface in L dotted with N plus mu. Okay, this gives me H plus P. Okay, so we have now if we consider a surface, a hypersurface M that has a mod that has a surface that satisfies H plus P equals 0, we want to use a parabolic flow, which will be the no mean curvature flow, to detect this surface. Okay, so I'm going to draw actually the same picture as before. So say here's my H plus P equals 0 surface. I want to start with a surface way out here, flowed by no mean curvature flow. So this would be motion with speed equals H plus P. And hope that I can let this t go to infinity, and the limit will be this guy. Okay. Now, in general, mean curvature flow, no mean curvature flow satisfies an avoidance principle. This means that if I start with two surfaces that are disjoint, then they will stay disjoint for all time. Okay. This has the following consequence. If I have a minimal surface, or a mod in this case, then the flow will stop here. It cannot pass this guy. Okay, this is like a result of maximum principle. Okay, so we want to do this thing, right? Like, say, write this equation for all time, take a limit as t goes to infinity, and detect the mods. Now, the big issue with this, when you try to do mean curvature flow or no mean curvature flow, is of course it's not gonna run for all time. The problem is that the right and very concrete examples. We already seen here the sphere. Okay, in this case, the mean curvature goes to infinity. Something has to happen to the flow. Where in the sphere it's okay because then the whole surface disappears. But there are other examples. The standard example is a dumbbell. Okay, this is even like a two-dimensional surface in R3. If you try to flow this by mean curvature flow, then something will happen. Okay, the surface will pinch here. And this can be seen because you can put big spheres here, and you can put a surface called the unguided torus. This is a self-similar shrinking torus to show that the torus will shrink before the sphere shrink. So this tells you that at some point your surface will pinch. Okay, and what happens here is that the mean curvature goes to infinity. Okay, so something happens to the flow, you cannot continue. So because of this issue, you cannot hope always that you're going to have a smooth flow with t here going to infinity. Okay, but what we do in this case is we forget about restricting only to smooth flows and go to a weaker sense. So there are many different weak formulations. Yeah.
This example and sigma.
Oh, here M is R3.
And there is no L.
Oh, yeah. This is also, like, this is just mean curvature flow, okay? So this mean curvature flow is the particular case where K equals 0. Okay, so this is like this time symmetric initial data set. But this is just to say that even like in Euclidean space, problems happen. Okay. Another thing that I forgot to say is that, of course, we can write down the evolution equations for all the geometric quantities, and this is something that is preserved under the flow, the same way that H is positive is preserved under mean curvature flow. Okay, so why this is important, because your surface only moves in one way. Okay? This is very important in the first weak formulation I'm going to write here, which is the level set flow. Okay, this was done by Evans and Sprague. And by Chen Kikagoto. I'll explain this in a second, what this means. So this is like one weak formulation. There is also the maximal flow. This was used a lot by Brian White and Ilmanen. And finally, probably the hardest one is the flow with surgeries. Okay, this was developed a lot by Husken and Sinestrari. And Husken Brendel.
What do you mean by the maximum flow? It's actually a different flow, right? Used by Millman.
Well, actually, in most cases, you can show that these are all the same. Well, actually, this is the same as you let the surgery parameter go to 0. But these two are the same. It's just like a different way of looking at it. So this maximal flow is defined only by the use of the avoidance principle. Okay, but the level set flow is also, you can define it for general things that don't have to satisfy H positive. But when H is positive, you can describe it in an easy way. Okay, and this is the one I'm gonna use now. Whereas the maximum flow says, okay, I'm gonna look at a flow that just satisfies the avoidance principle with any other smooth mean curvature flow. Whereas the level set flow, we can write it using a PDE. So what does this let find a function u? So omega will be such that the boundary is your initial surface. Okay, so omega is the region that is enclosed by the initial surface, and you want to find a function u over omega that satisfies the following. The level sets of your function u will be exactly the surface is sigma t. So in the case of a shrinking sphere, okay, I'm just going to do the one-dimensional thing. So you have, or like say here, a shrinking circle. What you do is you want to find a surface over the original circle. So you go and you put the surface sigma t. So this is what happened to sigma after time t. You go and put it at height t. Okay, and this creates a function u, okay, defined over omega. Now, I'm going to put this omega in quotation marks because this is not really true. This happens as long as you don't have a minimal surface inside. If you have a minimal surface inside, then this function u should blow up at this minimal surface. Okay? So in the case, in this example, where you expect to have like a flow for all time converging to a minimal surface, then, okay, if this is your omega, and somewhere here is your minimal surface, then your u should go and blow up on the minimal surface. Okay, same thing with the Normand curvature flow. Here will be a mod. Your surface will blow up on the mods. Okay, this is the expectation. Now, by looking at this definition, the function u has to satisfy the following. Since the level sets flow by mean curvature flow or Normand curvature flow, we have okay, so this is for mean curvature flow. This is the divergence of the normal to the level set. So this gives me mean curvature flow. Mean curvature. So this is mean curvature of level set. And this guy here is the speed. Okay, this is the speed of the level set. Okay, in Normand curvature flow, we have an extra term, this p, which remember is the trace of k over sigma. So I get okay, so this is the p term. So this is the trace over sigma, the level set of k. All right, so this is the equation that we want to look at. Let me write a star. Okay, so we hope to solve this equation. And there are two problems. So first is the issue that the equation is degenerate. So I have this du by itself on the denominator. So when du goes to 0, there's a problem. Yeah?
Case or conditional?
Oh, I should put, okay, maybe I'll write them as, okay, this should be the connection on M. Better? Right, so this will, so u here will be a function from a subset of M to R. Okay, so the problem one, as I said, is that we have this degeneracy. And the second issue is, which is what is important in our work, is to find the domain over which the solution okay, so finding the domain of definition would be actually detecting the mods, okay? Because on the one hand, you will have the outer boundary, which is your initial surface, and you want the other boundary to actually be the mods. Okay? So what we want is that the boundary of, let me call it, so the domain of definition omega 0 in general would be a subset of omega. And what we want is that the boundary of the domain of definition without the initial surface, we want this to be the outermost mods. Okay, so we want it to be a mod, and it will be the outermost. We have to show this because of this avoidance principle. Okay, so that the flow cannot cross another mod. Okay. So to deal with the first problem, the fact that the equation is degenerate, we're going to do what is called the epsilon regularization trick. Okay. And this is done by approximating this equation with another one that adds a little epsilon on the denominator so that you don't have this problem of the gradient going to infinity. Okay, so we write the equation as follows. I'm going to write this as star epsilon J epsilon, again adding an epsilon down here and on the right hand side. Okay, so now the equation is a nice equation without a degeneracy anymore. Okay, now if we scale this solution, if we consider if we scale this equation by a solution by epsilon, then the equation will take a form that is very familiar. So this I'm going to write it as epsilon hat. Okay, so the equation becomes this one, and the left-hand side, if I forget the k, this is the minimal surface operator. And with the p, this is known as, with the right-hand side equals 0, this is known as Young's equation. Okay? And this is like a very good sign because this was already used by Shen and Yao to show that the positive mass theorem, and they use this equation with the right-hand side equals 0 to say, okay, when this equation blows up, it blows up over mods. Okay? But even with this guy here, there's not going to, hopefully there's not going to be a problem because when it blows up, this guy goes to 0, okay? Because the gradient goes to infinity. Okay, so this is the equation that we have to solve here because we want to take advantage of the fact that we had this parabolic flow at the beginning. We will use the theory as well of as developed by Evan Sprague. And what do I mean by this? We have the following fact here. If you look at these guys, epsilon over epsilon minus t over epsilon, and all mean curvature flow. So this is a translating solution of null mean curvature flow. Okay, so we have these graphs, and if you start translating them down with speed t over epsilon, then they satisfy mean curvature or null mean curvature flow in this case. Okay. This means that the function, in other words, the function so this function capital U, this is defined in a space of dimension +1. This is a solution of this equation, okay? Because the level sets of capital U epsilon, they satisfy smooth mean curvature flow or null mean curvature. Okay, so we will keep this in mind because we'll have to use this as well. Okay, and just to draw a picture of what is happening. Okay, so just to draw a picture here, say this is my outermost mods, and this here is my original surface. Then we hope that this will be our domain omega 0, and what will happen is that this U epsilon will look like this. Okay, and as epsilon goes to 0, we want these guys to converge to a solution U, which will be a solution of our first equation. Okay? Now, each guy here, when you scale it by epsilon, it goes to something that is vertical. Okay? This vertical thing would be the level set of U. Okay, if this makes sense. And each guy here, U epsilon, when you scale it, so you have U epsilon and you scale it. This, if you start translating down, this satisfies smooth mean curvature flow or null mean curvature flow. Okay? And for each t, so if I take this guy here, say U epsilon minus t over epsilon, and you let epsilon go to 0, then what happens, it goes, this will tend to a cylinder. The cylinder will be the t slice of your U. Okay, so there are two ways you can see this problem. You can try to look at this U epsilons and take a limit, or try to solve the equation. Okay. Now solving the equation is easier because it's already done by Shen and Yao. Okay. And the way that they solve this equation is by adding a capillary term here. Okay, so call this then. Okay, so the problem with this equation without the capillary term is that if you try to solve it, this is a quasi-linear equation. You know, you look at Gilbert and Trüninger, the first thing you have to do is try to find sup estimates. But because of this term here, there are no sup estimates. However, when you add this term, you can actually prove that this new equation with the kappa has sup estimates. Okay. Okay, so let's solve this equation. Okay, now you can see the idea, right? That if you look at this equation, this will be, we'll have, you're first going to let kappa go to 0, get a U, you want to let epsilon go to 0, and get a solution of the level set problem. Okay? So, yeah, let's first solve the equation with the kappa. As I said, if you look at this equation, there is, without the kappa, there is no maximum principle, but with the kappa, you have sup estimates. Okay, that you can get by a standard maximum principle. Okay, I mean, like you go to a maximum. This is a sign. Here you get a term that has a bound by the eigenvalues of kappa, of k. And here on the right-hand side, you get kappa times the sup. So this altogether gives you a sup estimate of the form this, okay? Of course, as either kappa or epsilon go to 0, this goes to infinity, but we don't mind. So you have sup estimates. Then to be able to say that you have a solution, you need gradient estimates and boundary gradient estimates. But these are fairly standard. You have gradient estimates, interior ones, again by doing a maximum principle. Yeah, this is fairly standard. If you do a maximum principle on a quantity like this, okay, once you have the sup estimates, you do maximum principle on a quantity gradient times e to the u. This gives you an interior gradient bound. And for the boundary, here we use barriers so as developed by Sarin for the solution of the Dirichlet problem. Okay, again, like this is fairly standard. For this part, we need H to be positive. Okay, not just H plus P to be positive, but H to be positive. That's why, like for the manifold M, we assume that it's flat enough at infinity so that I can start by something that has H positive and H plus P positive. Okay, so doing all this implies that there exists a solution u kappa epsilon of the equation star kappa epsilon. Okay, so for any given an epsilon, we can find a solution for any kappa. Okay. Right. Now, the next step is to take a limit as kappa goes to 0. Okay. Now, as you see by the supremum estimates, the problem with taking kappa go to 0 is that the sup will go to infinity. Okay. But this is bad, but it's also good because it shows that the domain of your definition is not going to be the whole omega, but the solutions that have to blow up somewhere. Okay. Hopefully in the mods. Okay. Again, this problem appears in the work of Shen and Yao, okay, because they do the same. It's exactly the same thing, but this term is not there. So what they do is instead of saying, okay, let me take a limit of the functions, they look at the graphs of the functions, the surfaces, have estimates on these surfaces, and take a limit as a surface. So we want to here take a limit for kappa going to 0. I'm not going to look at the equation. The function u kappa, but I'm going to look at g kappa, the graph of u epsilon kappa. Now, why this is convenient? Because if you look at this surface has uniformly bounded mean curvature, independent of kappa. Okay, so this is the mean curvature by this term, which is bounded, and this one is bounded because this is the bound for the sup. Okay, so the sup goes like 1 over kappa, so kappa times the sup is uniformly bound. Okay, so these guys here have uniformly, in kappa, bounded mean curvature. Okay, but such surfaces, when you have graphs that have uniformly bounded mean curvature, they are what we call almost area minimizing and satisfy really nice compactness properties. So actually they're almost like being area minimizing. Okay, so let me draw another picture. So here's again, this is my omega. This is the initial surface. And these solutions U epsilon kappa, they're defined over all of omega. Okay? But they go to, as kappa goes to 0, they start blowing up somewhere in the interior. The boundary gradient bounds, they are uniform. Okay, so this last estimate, these are uniform in kappa. So we know that even if they blow up somewhere, at least there is some portion where they stay bounded. Okay? And we also have this. This means that, as I said, that the G kappa, they are almost, or let's call them lambda area minimizing. Okay, area minimizing would be, okay, here's my surface. If I change it here at some compact set, then the area will go up. Lambda area minimizing means that, okay, the area might go down, but in a controlled way. And the controlled way is given by the volume of the in-between region. Okay, so call this F. This means that the area of GK is less than the area of F plus lambda times the volume. Let's call this U. Okay, so the area might go up, but in a controlled way. Such surfaces, they have, as I said, very good compactness properties, just as good as the area minimizing surfaces. In particular, they have uniform C1 alpha estimates. Okay, this will be uniform in kappa. Okay, but if you have C1 alpha estimates, you go back to your equation, and because the right-hand side depends only on the gradient, you have uniform C infinity.
When you use the compactness theorem?
Sorry?
When you use the compactness theorem, do you still get a graph so that you can represent using a function U?
Yes. So you can, well, I'm skipping a bit of details, right? But you can, here, if you look at the normal, okay, you can apply a Hopf maximum principle at the normal that tells you that the limit is either a graph or vertical cylinders. Okay, this is done at the Shen Yao paper as well. In this case, by the way the equation is, what you're going to get is just a graph over a domain that part of its boundary is sigma 0. Okay.
These uniform estimates are like local, not vertical.
Exactly. So these are C1 alpha estimates as a surface. Okay, so this implies that I can G kappa, as kappa goes to 0, has a smooth limit, G, which is a graph of a function U epsilon. Okay. Now this U hat epsilon is defined on some omega epsilon, has part of its boundary, this contains sigma 0, the initial surface, okay, which is the boundary of omega. Okay, now what I get here for U hat epsilon is something like this. Okay, this is my U hat epsilon, where here the one boundary is sigma 0, and the inner boundary here is the one that I don't know. Okay, so this is omega epsilon. Now, doing the exact same trick, but looking like this U hat epsilon, looking at the graph and starting translating downwards. Okay, so if you look at U hat epsilon minus a, start and let a go to infinity. then what will happen is what are you going to see? This starts translating down. So you're only going to see the boundary. Right? So this converges to the boundary, the inner boundary, okay? Cross R. Okay, so the limit of translations, they give you the boundary of the domain. And arguing as before, by using like the uniform estimates of these graphs, you can show that this guy is a smooth surface, and looking at the equation, you had epsilon satisfies this equation. Remember, this goes to infinity, so what you get is a mod. Okay, you get this limit as a goes to infinity should be a solution of this equals 0. Okay, so this implies, remember, this guy solves star epsilon hat. So this guy here has to be a mod. Okay. Again, because these uniform estimates, they allow you to take a limit. The limit is smooth. You look at what the equation satisfies. The limit has to satisfy the same equation. Okay, but the gradient goes to infinity, so this goes to 0. Okay. Well, I mean, maybe, so just so that it's not confusing, maybe you think, okay, this goes to infinity, this goes to infinity, everything goes to infinity. But this is actually the mean curvature of the graph. Okay, so you just see it as mean curvature of the graph. This guy here is the p term. So you can see this here as Gij minus mu I mu j kappa ij, where this now is the normal to the surface. Okay, so this is not, then you forget about the things being graphs. You look at it as mean curvature plus the p term. And this is how you take, you look at this quantity on this graph, and when you take a limit, the right-hand side goes to 0. So h plus p for the limit is equal to 0. Okay, so remember what we're doing? We took an epsilon, then we made this, we added this capillary term with the kappa and took a limit. Okay. And this gave us a solution for each epsilon. Now, we want to show that this mods here is the outermost mods. Okay, and if we show that it is the outermost mods, then it's independent of epsilon. Okay, it's always the same guy. Right, now, this is a little bit technical, so I'm just going to sketch it. But the idea is an idea of Metzger and Anderson that showed that very close to the outermost mods, and on the inside, there exists a surface that satisfies h plus p negative. By changing the data a little bit and using the fact that this is stable, so there is a notion of stability for mods, and the outermost one is stable. By using this fact, they were able to change the data inside a tiny little bit to say that here, very close, I have a surface that satisfies h plus p negative. Okay. Now, using the flow and the avoidance principle, once you have this guy, you can create a nice barrier over this surface. Okay? And the way to do this is that when you look at mean curvature flow or null mean curvature flow, there is always a solution, a smooth one, for a tiny little bit of time. So using this solution, you can actually create, I mean, it's not so easy, but you can find a function that serves as a lower barrier for the kappa solutions. Okay, so what you do is you create, and you find the barrier by using the flow. Okay, the flow gives you a solution for the, I erased it, but for the level set flow for a little bit of time. Okay, because the gradient is never zero for a little bit. Okay, so this allows you to create a barrier here above this H plus P negative. Okay, remember this is a condition that is preserved under the flow. So when you start flowing this guy, it's going to start flowing towards the outermost mods. So you use this flow to create a barrier here that becomes as big as you want and lies underneath every solution kappa. So taking, using this lower barrier, you can show that actually your U epsilon has to blow up above this H plus P negative. Okay? So this barrier construction over the surface H that satisfies H plus P negative gives you that the boundary of omega epsilon is equal to the outermost mods union sigma 0. Okay, the original surface. Right. So this now is already a way that we have located the outermost mods. Okay. So this is the inner boundary of this epsilon solution. Okay. However, well, I mean, I don't know much about this numerical analysis, but apparently it's much easier to use parabolic than elliptic things in numerics. So this is not good enough. You want to say that the flow actually goes to the outermost mods. So what you want to do is be able to take a limit of U epsilon and say that the U solution, the limit, also blows up on the same guy. But now what happens, and there's like a big problem with this. Okay, here are your U epsilon. First of all, we have to show first that you can take a limit of this U epsilon. And second, then the limit might be blowing up somewhere else. Okay, so you lost the outermost mods. So let's first take a limit of the U epsilon. Okay, these are more and more estimates, so I don't want to bore you with that. The trick is again the same. Okay, look at the surface, do a gradient estimate, boundary gradient estimate. Now, of course, there is no sup estimate, so the best gradient estimate you can show is that the sup of grad U epsilon is bounded uniformly in epsilon, but where? Over x's such that U epsilon is bounded by some constant. Let's call it lambda. Okay, so this would depend on lambda. So this means, okay, if you cut and hide lambda, here you have a limit. But you can do this for any lambda. Okay, so again, this means that you get a, you can take a limit as epsilon goes to 0. Okay, and this subset is not empty because you have uniform boundary gradient bounds. Okay, again, you do, this is like a very common trick in the level set flow, where you use a smooth flow of the boundary to create a barrier at the boundary. Okay, so you use a smooth flow for a little bit of time of the outer boundary here to create something here that is always above every solution, but it blows up very close to the boundary. But this allows you to say, okay, I can take a limit as epsilon goes to 0. And this will give me a solution of the level set flow. Okay, so you can, this here implies that you can take a limit as epsilon goes to 0. But now this limit will be defined in some omega tilde, a subset of omega epsilon. Will be a solution to level set flow. Okay, this was the original degenerate equation that I wrote. Now, if you look here, what is this convergence? The best you can do is C0. Okay, because you have only gradient estimates. So this is like a C0 convergence. This guy here is Lipschitz. Okay, but now you cannot go more. Like you cannot use PD to say anything more. Okay, and this U epsilon, the boundary contains the original sigma 0, but this is all you know. And now there is, once you're done with all these PD estimates, then you have to go back to the fact that these graphs, you remember I was saying at the beginning, they satisfy mean curvature flow. You have to exploit this fact to now be able to say something about the inner boundary of the level set solution. Okay. And the way you do this is by using a lot of geometric measure theory. Okay? Because now things are not smooth, so you have to use geometric measure theory. The big, the most important fact is that these graphs have a uniform L2 bound on the mean curvature. Once you have a uniform L2 bound on the mean curvature, when you see these surfaces more general as varifolds, and this is the correct way to look at the surfaces, you can get nice limits. Okay, so you need more than L1. L2 is good enough to say that, okay, I can take a limit of the surfaces, and these surfaces will converge to something that has a mean curvature. Okay? Right, so the first thing is that, how am I going to write this? Okay, let me write as G epsilon. This is the graph. Okay, G epsilon. Okay, if you look at the graph of this, the scale U epsilon minus T over epsilon, remember these, they satisfy mean curvature flow. These guys have uniform L2 bound of the mean curvature. Okay, you can actually integrate twice in time and in space. Okay, so this gives you a region where the mean curvature is bounded in L2. Okay. This is one very important fact. And the second one is that these guys satisfy a minimizing property. Okay, what happens in mean curvature flow is that because the flow goes in a direction that minimizes area, the surfaces that minimize area on one side. So if you look at this U epsilon graphs and you change them on the outside, now you cannot move in this, just on the outside, the area goes up. But this is a mean curvature flow. Here you have area plus integral of P over the volume. So this goes up. So this is one-sided minimizing property, area plus integral of P. Okay? It turns out that this P term doesn't hurt you that much. You can use this minimizing property to say that now, okay, I can take, when I take limits as epsilon go to 0, this G epsilon T graphs, they converge to sigma T cross R. Okay, this is epsilon goes to 0. So this is a level set of U cross R. Okay, these guys now inherit this minimizing property. So now you have a limit of surfaces is sigma T, the level sets of U, that converge to something. Okay, because of this, and the P term is also bounded, you can show that in the limit, H plus P has to be 0. Okay. Of course, I'm skipping a lot of details, but that's the main idea. Okay. So once you have that H plus P equals 0, then you can show that sigma T, they converge to a mod. Okay, and I put this in quotation marks because the convergence is a measure theoretic convergence. So the limit is only a weak limit. So first, what we could show, and actually in our work with Kristen, we just left it like this. We said that H plus P equals 0 almost everywhere. Okay, and then we left this question open. We said, okay, could it be that, of course, this is outside the outermost mods, okay, because remember, this is defined somewhere with a subset of omega epsilon. And then we said, could it be that you have something that is stationary outside the outermost minimal surface? Okay, something that is outside the outermost mods that satisfies H plus P equals 0 almost everywhere. Okay, and last year, actually, this guy is a undergraduate student, actually, in Tennessee. He worked on this thing, and it's like we realized that it's not so difficult with a blow-up argument to show that this cannot happen. So actually, this guy we can remove. It's the outermost mod. Okay, and this gives you the result. Okay, that you get a level set flow that blows up on the outermost mods. So this is like a parabolic way to get your outermost mods. And to finish, let me just say that, just to write some reference, that everything here, this is inspired by the work of Husken and Illman, and that they did this whole program of looking at the weak formulation, this level set formulation, for inverse mean curvature flow. Okay, so this is the paper where they proved also the Riemann-Penrose inequality. And Kristen, in her thesis, she looked at the same thing, but with the P term. Okay, so there was the norm inverse mean curvature flow. So this was the part left. What happens, in the flowing forward, like the norm in curvature flow case that we looked at. And I guess I'll stop here. Thank you.
Other questions?
So you say you're assuming that your manifold is asymptotically flat, right?
Mm-hmm.
Are you assuming constraint equations, dominant energy conditions?
Well, you see, for me, because I don't know much about the GR behind it, like you can forget about everything. You can look. You only are interested in being able to say that way out, somewhere I can find a surface that satisfies mean curvature is positive.
Okay. So you didn't put any conditions on K?
No, there's not. Yeah, and in general, like this, okay, this GR is like the motivation why to look at this problem. But now, we forget about this. K could be any two tensor, as long as it's bounded, okay, and smooth.
More questions? So you had mentioned earlier that one of the reasons you wanted to go all the way to the point of showing that and that was why you were going all the way to the point where you're taking the epsilon 0, because before that it's effectively elliptic question.
Right. Yeah, that's what people had told me, that it's easier to, have something and flow it with a computer rather than trying to solve an equation.
So you were talking about for the lambda almost minimizing, and you said that it was C1 alpha.
Mm-hmm.
Do you ever get C11 for like maybe some dimensions or something?
Well, here you get C infinity, right? Because the equation is like.
I just mean like if you just have a lambda minimizing thing.
Oh no, C1 alpha is the best. C1 alpha is the best. You cannot get C11.
Even for certain dimensions, even for like dimension 2 or dimension 3.
No. And actually, I forgot to say that here everything is like for dimension like less than 7 because of this C1 alpha minimize, the almost minimizer.
Mm-hmm.